We left off in the previous slides with a description of the matched pairs paired differences setting. Now, in this setting, you have either the same person with two separate observations, or you have two people that are plausibly from the same population that are matched together. So, just a recap of the semantics, the matched pair is a before and after for the same individual. The paired difference is pairing, think of it as a verb where you're pairing two people together. And at any rate, what we do is we construct a difference in either treatment versus no treatment, or saw campaign A versus campaign B, or a policy change, or perhaps a before and after. We we look at two separate pieces of information and we take the difference, we subtract. That difference is the observation. So two data points are combined into one observational difference. Once we have those sets of differences, we can take the average of the differences, we can find the standard deviation of the differences. Yeah, certainly we can count the differences, and we have enough information to test a hypothesis, but the hypothesis that we're testing for the purposes of this class is just that there is no effect. So the policy has no effect, the treatment has no effect. It doesn't matter whether you see A or B, there's no difference before and after. So if I take one grouping and subtract the other grouping, no difference implies a mean difference of 0. And then the alternative is that there might be some difference. So we're going to continue with this concept today as we examine two other hypothesis test settings. The first is what's called a pooled sample. So this is where we have two separate populations. With the matched pairs, paired differences, you are drawing out of the same group. Either, literally you have the same person just measured at two different periods of time, or you have a group of people that is plausibly similar in every way except for the treatment. With this new setting, which is called pooled, we do have two distinct groups. So I can't draw one person out of one group and another person out of the other group and say that, hey, these are exactly the same population, but they may be very similar. So when I teach stats 2, I often teach the class at 11 o'clock and then right around at 12:30. Those are technically different populations, but they, for all rights and purposes, may be very, very similar. And we may want to do what's called pooling the sample. So because these groups are so similar to each other, we can use some statistical techniques to pool the standard deviation. So in the matched pairs, we combine the data points into one observation and we just have one standard deviation. But with pooled, we have two separate standard deviations, and we're going to take a weighted average of those standard deviations to construct one standard deviation. And that's listed right here. It's called the standard deviation of the pooled test statistic. This is S squared. This is actually called the pooled variance. So how it works is you have two different populations. So when you compare them in some way, you have two different means, two different sample sizes, and two different standard deviations. Those sample sizes may be quite different. So, on the slides I have 11 and 12:30. Let's say you even extended it to like 11 and 3:30. Whenever I teach at 3:30, attendance is sparse, even if I have the same number of people enrolled. So I may have a small sample for the 3:30, but when I teach at 11 o'clock, people show up. Okay? And so I may have differences in sample sizes. I can combine those differences to make one standard deviation. So I do it with this pooled variance here. N1 is the number of observations in the first group. N2 is the number of observations in the second group. S1 is the standard deviation of the first group and it's squared. S2 is the standard deviation of the second group squared. The reason we pool the sample is so we can increase the sample size. So when I pool the sample for statistical purposes, my degrees of freedom are n1 plus n2 minus 2. The minus 2 comes from n1 minus 1 plus n2 minus 1, and then you have 2 minus 1s, that gives you minus 2. So long story short, oftentimes when we're testing a hypothesis, when we think the groups are pretty similar, but uh, they are technically from different populations, we often like to combine the sample sizes into one pooled sample size. And you can see that here with these degrees of freedom. From a practical perspective, the type of hypothesis that we test for a pooled sample is identical to the type of hypothesis that we test for a matched paired differences setting. So when I have these two groups that are plausibly similar and I've pooled the sample, I'm testing to see whether the mean difference is 0. So the mean of the 11 o'clock is the same as the mean of the 12:30. And so when we have a pooled sample, we're still comparing two groups. We set the mean of group 1 equal to the mean of group 2 in the null. So the implication is that the difference is 0. Mu, this parameter, when I take the mean of group 1 and subtract the mean of group 2, that's captured with this mu, and we're assuming in the null, we're testing that it's 0. Now, there could be an inequality, so the context clues still relate. If I have a less than hypothesis, then the null will be greater than or equal to, but we're always going to be looking at 0. So for the matched pairs, the pool, and what we're going to look at here in a minute, the two population, we're always testing to see if the two groups are equal to each other. Now, when you're actually doing statistical analysis, this is actually often the test that you do then too. So this is a bulk of the time the type of hypothesis test that you'll do. Because we pooled the sample, we're assuming that the standard deviations are not too different from each other, that they have equal variances between the groups. So we're testing to see whether there's a difference in the means, but the shape of the bell curves is assumed to be the same shape. Maybe the means are different. Okay, so how do I know when to pool the sample? In this class, I just tell you to pool the sample. If I don't tell you to pool the sample, don't pool the sample. So because it is so subtle theoretically about when to pool the sample, in this class, I'm just going to tell you to pool the sample. So let's have a look at the test statistic. The test statistic, I compare a sample difference in the top to 0. Sample difference to 0. I include the standard deviation squared of the pooled variance. So I have this S pooled here that's plugged in, and then I have 1 over n1 plus 1 over n2. Okay, so this is a fairly complicated test statistic, and let's have a look at how it works here. So suppose I'm just seeing whether there's a difference between an 11 o'clock class and a 3:30 class. I examined 45 test scores from the 11 o'clock class and 40 test scores from the 3:30 class. So the sample sizes are kind of similar. The mean of the 11 o'clock class is 83.2. The mean for the 3:30 class is 76.2. Standard deviation for 11 o'clock, 12.3. Standard deviation for 3:30, 12.1. How do I make the test statistic? I'm going to show you right here. So let's zoom in, even a little bit more. Here is the test statistic. Okay, the mean differences are at the top. So I have the 11 o'clock class go first, the 3:30 class goes second, and all I want us to think about here is that one of the groups has to go first. So this is the sample mean for 11 o'clock, it's 83.2. This is the sample mean for 3:30, it's 76.2. Okay, in the bottom, I have the pooled variance. Let's remember the formula for the pooled variance. It's this S squared pooled. So I have N1 minus 1 times S1 squared in the top. Okay, N for the 11 o'clock class is 45, minus 1 right here. 12.3 is the standard deviation for the 11 o'clock class, and it's squared. So that is where the first part of this formula comes from, this part right here. I do the same thing for the other groups. I have 40 in the 3:30 class minus 1 times 12.1 squared. Here is where I combine, this is where the pooling goes on. I fuse the sample together. So think of this as a weighted average where just a little bit more of the variance is coming from the 11 o'clock class because we have a slightly larger sample. Then I have 1 over N1 plus 1 over N2. Okay, so let me go to Excel and just show you how best to approach calculating this test statistic. So here's the information in the problem. 83.2 is the 11 a.m. mean. The standard deviation was a 12.3. Sample size was 45. This is the information for the other sample. Note that the standard deviations are pretty close, so the pooled is not a bad idea here. Okay, test statistic. Let's look at the pooled variance. I have N1 minus 1. So N1 is the sample size for 11 o'clock minus 1 times the standard deviation squared. So this is the first sample. I'm going to put this all in parentheses. Now, I'm going to add the second sample. I have 40 minus 1 times this standard deviation squared. That is the top, and then I have N1 plus N2 minus 2 in the bottom. This is the pooled variance. You can see here I compute the numerator of the pooled variance. Here I compute the denominator. Then I have an additional part of the formula, 1 over N1 plus 1 over N2. So I do that here. You can see I have 1 divided by N1 plus 1 divided by N2. You can see I generate both of these on the slides. I have 148.997 for the pooled variance and 0.047 for the 1 over N1 plus 1 over N2. Now I take the square root of this times this. That's the denominator. The numerator is the mean difference between the groups. The t-stat is the numerator divided by the denominator. And you can see I get this 2.63 9. Now, I'm going to reject the null. I know it says would not reject the null. I should reject the null here. So this is just a typo on my part. In fact, let me highlight this. And maybe I can scratch through it. I'm just going to highlight it here. And we will reject the null, so 2.639. If I go to row 80 in the t-table, exceeds almost all of these critical values, and in fact, it's almost identical to the 99% value, bigger than the 90% value, or 99% value for row 90. Okay. Please look at the pooled test statistic description on the hypothesis testing fact sheet. On the test, I will have you click the correct pooled test statistic setup, but I will not have you calculate the pooled test statistic because it is cumbersome to calculate. Okay, Excel will do this for you. In fact, we could do it with the same data that we had previously. You just have to go to data analysis, data analysis, equal variance. And that is the pooled test statistic. So when do we use the pooled test statistic? When I let you know that the setting is pooled. Sometimes we cannot combine the samples. So occasionally you want to test a hypothesis that means between different groups are distinct. This is what's called a two-population test statistic. So consider the mean study hours for females versus males. There may be a statistical difference, but it's a large stretch to say that the population of males behaves that similarly to the population of females. There may be quite a bit of difference in the dispersion. In that case, pooling the sample is out. So if I have two standard deviations and it doesn't tell me to pool the sample, I want to use a two-population test statistic. Mu is going to be the difference between groups. It could be male, female. It could be different states. It could be different countries. There are any number of circumstances where I think I'm dealing with two different populations. You can think of different differences along income levels, race, gender, age, any of those things. I think I'm in different groups. The null is that the mean is equal to 0. The alternative is that it's not equal to 0. You could have a greater than or less than. You just want to set it up accordingly. The test statistic looks like this. Same as the pooled, same as the matched pairs, sample difference in the top, a little bit easier than the pooled. So you can see here that I have split the standard deviations. I've split them up. So I'm not trying to fuse together different samples. Now, the downside is that the critical values are more conservative. So you pick the smaller sample size minus 1. You could use other methods in other books, but this is the most conservative approach. Okay, so let's take a look at one of these. Suppose you want to know whether there's a statistical difference in earnings between students in Georgia and students in Alabama. So statistical difference, think about it from the one sample mean. Does it imply a one-sided or two-sided hypothesis? So think for a minute. You should come to the conclusion that it implies a two-sided hypothesis. Statistical difference does not indicate the direction. So I start with the alternative like I did before, and I say that the mean of Georgia is not equal to the mean of Alabama. And this, at the same time, means that the difference between Georgia and Alabama is not 0 because they're not the same. So the mean difference is not zero, not equal to zero. That's the alternative. There's always an equal sign in the null. So statistical difference, it shows up in the alternative. Okay, so now let's test this hypothesis. I sample 35 people from Georgia, find an average earnings of $13.41 per hour, standard deviation 356. You sample 42 people from Alabama, sample earnings of 1211, standard deviation of 483. So there's a $1.30 difference in the sample. Is that statistically different from zero? So what we're trying to do here is just ask whether the $1.30 difference that I see in this sample is large enough statistically to rule out no difference whatsoever. And it's not obvious that it is because there's quite a bit of dispersion in Georgia. So the standard deviation in Georgia is $3.50, and the standard deviation in Alabama is $4.83. So there are plenty of instances where individuals in Georgia earned less than individuals in Alabama within the dispersion of our different data sets. And so that's why we're testing this hypothesis, because the $1.30 may not be enough. Okay, so let's try it out. Here's the test statistic, difference between the two groups in the top, and we've got the dispersion and the sample sizes in the bottom. Okay, so let's go back to Excel. Here's the Alabama mean, Alabama standard deviation, Alabama sample size. Okay, and now we have the Georgia mean, the Georgia standard deviation, the Georgia sample size. If there is no opinion about the direction, it doesn't matter which one goes first. If you think one is larger than the other, I have the bigger one go first. Okay, so Georgia, 1341, 356, 35. Alabama is 42 is the sample size, 1211 is the sample mean, and 483 is the standard deviation. Now here's the t-stat numerator, just the difference between the groups. Alabama minus Georgia, Georgia minus Alabama, the only thing that's going to change is the sign. The denominator, I take the square root of, I put in a fraction, the standard deviation, let's do Alabama first, squared divided by the sample size, plus Georgia standard deviation squared divided by the sample size. That's the denominator. The t-stat is this, minus 1.36. We go to the critical values are from row 34. Now we could use T inverse to get a critical value. This is two-sided. I make it negative, so our test statistic is larger than the negative critical value. We don't reject the null. You can see that I put the critical values on the slide of 1.691, and actually Excel looked that up for us. So that's a plus. A couple comments about the two population. I think this is the preferred test statistic for comparing two groups. So unless you have some really obvious reason to pool, you should use this test statistic. In Excel, very easy to use the test statistic. Type in the data for one group in column A, the other group in column B, and then just click to sample, assuming unequal variances. The hypothesized mean difference is always 0. All three of these settings, the matched pairs, the pooled, and the two population, the hypothesized mean difference is 0. So that is a commonality between these groups that we want to use.